Hello everyone.
Step into Wix.
Okay. I hope that you are all well. Can you hear me? I would appreciate it if someone can confirm if you can hear me and see me well. And if, okay, awesome. Okay, how's it going? Is everything fine? Guys, right now it's 8 a.m. here. What time is it in your country? What time is right now for you? No, pretty much, it's very soon in the morning right now here. Hey, Aryan. 5:30 p.m., 3 p.m., 8 a.m. in Bolivia, so you're in the same time. Salam Aura. 5:30 a.m. Okay. Nice. So, guys, today in our live stream today, we're gonna solve some problems from number theory. We had two topic streams recently on number theory, and now it's time to try to solve some problems using the things that we've learned so far. So I'm gonna go over all these problems and I'm gonna explain all the solutions. We're gonna start from easier problems from difficulty around 1500 and go to difficulties over 2000. But all the problems are in a way that I'm pretty sure that all of you can understand. I chose the problems that do not need much prior knowledge, and I can easily explain it to you, and I'm sure that you will all understand the solutions to all of them. And that's what makes these problems very interesting. So if you are all ready, we can start and talk about these problems. It's 5:30, guess the country. I guess it is India. Because there are a lot of 5:30s, and each tag is best to develop observation skill. There are several, if you choose any tag, there are several observations that we can have in every text, but usually maybe ad hoc problems have more observations, but we're gonna see. Sometimes DP problems have a lot of observations, sometimes graph problems. Each tag can have a lot of observations, and at all problem solving helps you to develop your skills. Okay, so shall we start? Are you guys all ready? Think everything is ready now. Yeah. Okay, nice. So let's start talking about the problems. Okay, guys. This is the first problem that we're gonna discuss today. Good sequences. It says that assume that you have a sequence A1, A2 to AN, and you want to choose that, you say that a sequence is good if it satisfies the following conditions. The sequence must be strictly increasing, and no two adjacent elements are co-prime. In other words, GCD of each two consecutive elements must be greater than 1, and all elements of the sequence are good integers. It means that they must be from these numbers. So you have a sequence A1, A2 to AN, you say that these numbers are good, and you say that you say that a sequence is good if and only if it is increasing, its numbers are from these numbers, and each two consecutive numbers, for each two consecutive numbers, their GCD is greater than 1. You have to find the length of the longest good sequence. For example, in this case, we can choose, and AIs are given to you in increasing order, and they are up to 10 to the 5th. In this case, we know that, we say that 2, 4, 6, and 9 is a good sequence. Because it is strictly increasing, it uses these numbers, and if you see GCD of 2 and 4 is 2, GCD of 4 and 6 is 2, and GCD of 6 and 9 is 3. GCD of each two consecutive numbers is greater than 1. Therefore, it is going to be a good sequence, and the longest good sequence will have length 4. So we have to find out the length of the longest possible good sequence. Okay. So basically we have these values. Let me also send the link of the problem in the chat. We have this sequence, these numbers, these are good numbers. It's like we want to find a subsequence from this sequence. And since we know that they are in increasing order, it's like we want to find the longest subsequence of this one, such that GCD of each two consecutive elements is greater than 1. We want the greatest subsequence, longest subsequence, such that GCD of each two consecutive elements is greater than 1. If you have any doubts about the problem statement, let me know in the chats. I assume that the statement is clear for you. Okay, at any point, if anything was not very clear, feel free to say it in the chat. I can explain them again. So, well, in here, when I want to find the greatest, longest subsequence that GCD of each two consecutive elements is greater than 1, there's an important point that I know. I know that AIs are up to 10 to the 5th. What I do is this. I can define some sort of DP. In this problem, not only number theory is important, but also I use the ideas of DP as well. I want to find out that I know that when I have a sequence right now, and I want to add another element to it, I know that the GCD of this one and this one must be greater than 1. I know that GCD of these two must be greater than 1. So I should know something about this last element in the sequence. This last element is important. It must be divisible by something that this one is also divisible by that. So I define some dp of I, which is the greatest length, the longest possible subsequence such that the last element is divisible by I. So dp of I is the length of the longest possible subsequence such that the last element of it is divisible by I. If I know this, I can iterate over all such i's. When I add some x, there is a divisor of x such that I'm sure that both x must be divisible by that. If I'm adding some x to the end of a sequence, I must find some divisor of x, like y, so y is a divisor of x, such that this last element is divisible by y, and x is also definitely divisible by y as well, because y was a divisor of x. Okay. So, and y definitely must be greater than 1, because the GCD must be greater than 1. So they must have some common divisor greater than 1. So basically what I do is this. I have a for on all the elements. Let me write pseudocode. I from 0 to n minus 1. All the elements that I have. I use zero-based indexing. Then I have a for on all the divisors of x. How can I have a for on all the divisors of x? We've talked about it already. I can do it in O of roots x. For example, if my number is x, I can do it in O of roots x. For example, let's now assume that we have a sub I. So I know that I can have a for j such that j times j is less than or equal to a sub I. I can have such a for, and I say that if ai modulo j was 0, then it gives me two divisors if ai modulo j was 0. Both j is a divisor of ai and ai over j is a divisor of ai. So this is how I can find all the divisor of a sub I. I have a for up to a square root, and I know that one divisor is j itself, one divisor is ai over j. And I'm sure that this way I will see all the divisors, because when I can write ai as the product of two numbers, x times y, y is equal to ai over x. Either x is greater than or equal to a square root ai, or y is greater than or equal to root ai. At least one of these two will happen. So, or I can say that at least one of them is less than or equal. It's better if I say one of them is less than or equal to. Definitely, one of them is less than equal to, the other one is greater than or equal to. I'm sure that one of them is less than or equal to root ai. So when I have a for up to root ai, and if ai modulo j was 0, I consider j and ai a sub I over j. I've considered all the divisors of ai. Then I say that my ans, let's define that I have some res. I define some res that is gonna be the maximum possible length that I can have, such that a sub I is its last element. My res is initially 1, I mean, because in the worst case scenario, this one can be alone. I can form an array only with this element, so at least it is 1. If this happened, I say that my res is max equal to is not really an operator, I'm just using it in this pseudocode, is equal to dp sub j, max equal to dp sub j, dp of j plus 1, because maybe the last element was j. And I should make sure that I have this situation only if j is greater than 1. When I say this, I say that if j was greater than 1, have this. And also res max equal to dp of ai over j plus I. Why I emphasized on that j must be greater than 1? Because there's only one pair. I mean, if j is equal to 1, we have 1 and a sub I itself. 1 must not be considered, but a sub I must be considered. So, I mean, dp of a sub I might be considered. So either you should start your for from 2 and consider ai at the end, or you should have an if that j must be greater than 1 when you are considering this one. So I can also start j from 2, and in here also say that res max equal to dp of a sub I itself plus 1. This way I have the maximum possible length such that a sub I is greater than, is the last one in it. And then again I have a for, again on all the divisors. On all the divisors I'm gonna have another for. So again, for j times j less than or equal to a sub I, I say that if ai modulo j was 0, dp of, I update the dp's, because right now I have another value that is working, I mean another possible dp. I have to update all the dp's. dp of j is max equal to res dp of I modulo j, I divided by, a sub I divided by j is max equal to res as well. because now res is also a possible DP such that the last element is divisible by these values. So DP of j must be updated, DP of ai divided by j must be updated also. So I again update these DPs. So the key idea of this problem was to define some DP of I such that it is the max DP, the maximum DP, the maximum length, such that the last element is divisible by I. This idea really helps us to solve this problem easily. And I is up to 10 to the 5th because AI's are up to 10 to the 5th. And this is how this problem can be solved. Is it clear? So, if it is clear for you, please use this emoji or put a plus in the text. Can you please show us top-down approach, please? Well, I mean, in this problem, I mean, it's not really top-down or bottom-up. I mean, what we are doing, it's not really that way, because for each I, for each a sub I, we update several DPs. So we go over several DPs. It's not like we build DPs from the bottom and go to top, go up, or we start from top and go to bottom, go down. The point is that we have a 4 on all the AIs. We have a 4 on all the AIs, and for each one of them, we just update several DPs. This is what we are doing. We have a 4 on all the AIs, and for each one of them, we update several DPs. And the point is that you had another question, that what is the time complexity? The time complexity is that we have a 4 on all the elements, and then for each one of them, we will go through all its divisors in here and in here. We go over all their divisors. Going over divisors is going to be O of root of that number. So it's going to be if our numbers are up to capital A here, n and capital A are both up to 10 to the 5th. N is the maximum number of elements that we can have. I mean the number of elements that we can have. A is the maximum number, the maximum possible value that a number can have. Our time complexity is going to be n times root A. Because we have a 4 on all the elements, and for each one of them we have a 4 up to root A. So in this time we can solve this problem. Okay, is everything clear now? Shall we move on to the next problem, or do you have any questions about this one? Nice. Yes, that's completely correct. We can also only consider prime divisors. Yes, that would also work. So basically, let me quickly say this as well. This comment was completely correct. We can also only consider prime divisors, and if we do that, we can have a sieve at the beginning, as we mentioned in our previous topic stream. We can have a sieve, and for each number, store all its prime factors. Store all the prime factors for each number. For each number. And then we know that the number of prime factors is not a lot. I mean, each number has a few prime factors. For example, when numbers are up to 10 to the 5th, we are sure that it has at most, for example, 10 prime factors. It's even less than that, maybe 7 or something. So each number has less than 10 prime prime factors. And we can store all the prime factors of each number. For each number, when we go over all its multiples in sieve, we can store that, okay, these numbers have this prime factor. We can push back to their vector this value. And then when we want to find the answer, when we have some x, instead of these 4s, we only have 4 we can have only 4 on the prime factors. We can have 4j over all the prime factors of a sub I, and say that rest max equal to dp of j plus 1, and then have another 4 and update those dp's. So yes, we could also only go over prime factors. This would also work, yes. Okay, awesome. And this way our time complexity would be better, because for each n we go over only its prime factors, and prime factors are, for example, at most 7 or something. Why I say that? Because if, for example, we have, 7 prime factors, it means that at least our number must be 2 times 3. In the least case scenario, the power of all those prime factors is 1, and they are the smallest possible prime factors. So it must be at least 2 times 3 times 5 times 7 times 11 times 13, and times, for example, 70. And I guess this must be greater than 10 to the 5th, because only these elements are greater than 1000, and the rest of it, if you can consider it. Also, I can include 23 as well. 19 as well. Because if I show that if I have 8 prime factors, if I show that by having 8 prime factors, my number is gonna be greater than or equal to 10 to the 5th, then I show that my a sub I can have at most 7 prime factors. So my time complexity is gonna be very good this way. Yes. So yes, you're right. Also 7 is also bad as well. Even if it is 7, as you said, we can combine 3 and 5, which is greater than 10, and combine 2 and 7, which is greater than 10, and each one of these is greater than 10 as well. So it's gonna be greater than 10 to the 5th. It's gonna be strictly greater than 10 to the 5th, so we have at most 6 prime factors. So each number up to 10 to the 5th has at most 6 prime factors, and our time complexity is gonna be much better than what it was before. Okay, so now let's move on to the next problem then. The next problem is this one, simple subset. It says that a tuple of positive integers x1, x2 to xk is called simple if for all pairs of positive integers I and j, xi plus xj is a prime. You are given an array A with n integers, a1, a2 to an, not necessarily distinct. You want to find a simple subset of the array A with the maximum size. A prime number is a natural number greater than 1 that has no positive divisors other than 1 in itself, and a subset is just, we know that's what subset is. Let's define a subset of the array A as a tuple that can be obtained from A by removing some, possibly all elements of it. So we have some elements. We have x1, x2 to xn, x1, x2 to xn. We want to find a subset of it such that the longest, the greatest subset, such that for each two distinct elements of this subset, like I and j, x sub I plus x sub j is going to be a prime number. So for each I and j, x sub I plus x sub j must be a prime number. So And xi's are not necessarily distinct. So maybe xi and xj are equal. I must be not equal to j. So what are the facts that we can say? What are the observations that we can say in this problem? Is there anything that we can say? Is there any facts, any observations? Yes, sure. I put the link in the chat as well. So, what are the observations that we can have? Well, first of all, we know that about prime numbers. We know that prime numbers are, let's say, usually odd. Prime numbers are usually odd, they're not even. So, about the prime numbers, we can say that they are usually odd. Why I say usually, what is the only counterexample of prime numbers being odd? What is the only counterexample of it? The only counterexample is 2. 2 is the only prime number that is not odd. So what we can say is that assume that we have at least 3 numbers. You can choose more than one odd number then, right? That's a very good fact. Yeah, we will talk about it. If, the point is that if you have more than one odd number or more than one even number, other than one specific case that we're going to talk about, other than that, it's going to be bad. Assume that we have at least 3 elements, at least 3 numbers. By pigeonhole principle, 2 of them have the same parity. So if you have at least 3 numbers, by pigeonhole principle, 2 of them have the same parity. And therefore, when they have the same parity, we can say that their sum is even. So this is important. If you have at least 3 numbers, 2 of them must have the same parity. 2 of them are either odd or even. We find 2 with the same parity. So their sum is even. So their sum must be 2 in that case. If they are greater than 1, it is a contradiction. So we cannot, the first observation is that if we exclude 1, 1 is special. We do not consider 1. The other elements, the other numbers, from the other numbers, let's say from the other numbers, you can choose at most 2. Only 1 is okay, because we might have 10 ones. If there was no 1, if we couldn't have numbers equal to 1, we could easily say that the number of possible numbers that we can choose is at most 2. If there were no ones, we would prove that we could not have at least 3 numbers. Okay, so if there were no ones, right now we could say that we choose at most 2 numbers, not more than that. But we should consider the case that we have 1 as well. It is important because it's possible that we will have 1 as well. If we consider that we have several ones, so there are 2 cases. Either we have 1, or we do not have 1. So let's write it like this. Either we have 1 or we don't. Either we have 1 or we don't have 1. In case that, first let's talk about the case that we don't have 1. If we don't have 1, the point is that our answer is at most 2. If we do not choose any one, we know that our answer is at most 2. Right? And since my n is up to 1,000 and ai's are up to 10 to the 6, my n is up to 1,000 and ai's are up to 10 to the 6. We can say that we can have a brute force. We can choose any two numbers. We can have, because we know that our answer is at most 2. We can have a 4 on I and a 4 on j, any two numbers, and we can just say that if ai plus aj was a prime number, if this was a prime, then our answer is exactly 2 with these two numbers. And because we know that we cannot make it better than 2, this is our optimal answer. If it was possible, we write it like this. Otherwise, our answer is 1. We can choose any elements. And because from one element you cannot choose 2 and add them, any element that you choose, it's okay. If you have only one number, you don't even have two numbers to sum them up. So there won't be any two numbers such that their sum is not prime. So any single number is okay. So you can have a 4 on every two elements and say that if ai plus aj was prime, then that is the answer. And how can we check that? We know that a sub I is up to 10 to the 6. So this sum is up to 2 times 10 to the 6. You can use sieve to find out for any number from 1 to 2 times 10 to the 6 if they are prime or not. You can have a 4 from 1 to 2 times 10 to the 6 for any number. Oh, sorry. I guess that it seems that you didn't have my screen. So, let me explain this part again. We have two cases. Either we have 1 or we do not have 1. If we do not have 1, we know that our answer is at most 2. And since our answer is at most 2, and n is up to 1,000 and ai is up to 10 to the 6, we can have a 4 on every two possible elements and say that if a sub I plus a sub j was a prime number, since our numbers are up to 2 times 10 to the 6, we can use sieve and really find that out, if any number from 1 to 2 times 10 to the 6 is a prime number or not. And then if it was a prime number, since our answer is at most 2, we have the optimal answer this way. Otherwise, if the sum of no two of them was a prime number, the answer is 1. And it's not possible to have our answer equal to 2. So in this case, our answer is at most 2. And this is solved. In other words, we have solved the case that our answer is at most 2. Because if our answer is at most 2, we can brute force. We can choose any two and see if their sum is at most, if their sum is a prime number, and if it was, we could print that out. So we solved the case that our answer is at most 2. Is it clear so far? If it is clear, please put a plus or use the emoji. This emoji. So, is it completely clear? Yes, I didn't switch the screen at the beginning. Sorry about that. So, this is about this part. If we don't have anyone, we do not choose anyone, we are sure that our answer is at most 2. Now, let's consider that we have 1. So we have several ones. If we have one, we will choose all the possible ones because there's no reason to not choose any of them. So we will choose all the ones that we have. We choose all the ones that we have. And then we know that we can't choose any other odd number. Because if we choose any other odd number, its sum with 1 will be an even number greater than 2, which is not a prime. So we cannot choose any other odd number, we can only choose even numbers, so we can choose at most one even number. If you choose two even numbers, the sum of these two will be even greater than 2, which is not a prime. We can only choose, so when we choose all the ones, we can only choose at most one other even number. So basically, we choose all the ones, and then we have a for on all the other elements, all the other numbers, and see that if that number, we have a for on all the possible x's, and we see if x plus 1 was prime, then we can also add these elements to all the ones as well, otherwise we cannot add it. This way we can easily find the answer. I mean, if this is, for example, we have c ones, if such a x was found, the answer will be c plus 1 this way, otherwise the answer is c itself. So this case can be solved easily as well, and the whole problem will be solved. So we have two cases, if we have one or we do not have one in our answer. And both cases are solved now, so the whole problem is solved. Okay, is it completely clear? For now, we're not gonna go over ID and set up stuff. But in future, maybe in a topic stream, we can talk about those things. Okay, is this solution completely clear? If you are clear, if it is clear for you, if you are completely okay with that, please again put a plus or use the emoji. If that's the case, we can move on to the next problem. Nice. Please explain again C and C plus 1. Yes, sure. I'm saying that assume that you have C ones. Assume that the number of ones that you have is C. I said that you can add at most one other number to these ones because you cannot choose any other odd number. You cannot choose any other, I mean, from the ones, you will choose all of the ones. All of the ones will be chosen. But from the elements other than 1, you cannot choose even odd numbers because odd numbers plus 1, odd numbers greater than 1, plus 1 are going to make even numbers greater than 2. So it's not prime. So we cannot choose odd numbers, and we can choose at most one even number because the sum of two even numbers again is an even number greater than 2, which is not a prime. So you can choose at most one other number other than this one. So if we have C1s, we can choose these C1s as an answer, and maybe we can add one more element to it as well. So we have a for on all the possible x's and see that if we can add this x to all the ones as well. In that case, the answer is going to be C plus 1. Otherwise, the answer is going to be C. There's an edge case where there is only one and there are no even numbers such that x plus 1 is prime. Yes. In that case, the answer is going to be the number of ones. If we only have several ones and we do not have any x such that x plus 1 is a prime number, the answer is going to be the number of ones. So I said that the answer is going to be C, maybe plus 1. So there's C, maybe this C will be plus 1. Otherwise, it stays as C if we have C ones. Your interview series are awesome. Awesome. Yes, it's been a time that I didn't have interview, but I will start having interviews again. soon we will have more interviews. So, is it clear now? Shall we move on to the next problem? Awesome. Okay, so yes, and in the other case, if we don't have one, we said that either we have one or we do not have one. If we have one, we have only one number greater than one. If we don't have one, we can have at most two numbers, and we will fix them and see that if they are prime. In that case, the answer is 2. If we find two numbers such that their sum is prime. Otherwise, the answer is 1, because any single element makes a good set, because there are no two elements to add such that to check if they are prime or not. So it's okay. Awesome. So let's now move on to the next problem. The next problem is 803F. I add it to here. 803F. Co-prime subsequences. So in this problem, we have a non-empty sequence of positive integers. I mean, we call a non-empty sequence of positive integers a1 to ak. Co-prime if the greatest common divisor of all elements of this sequence is equal to 1. So it's co-prime if the GCD of all the elements of this sequence is equal to 1. Given an array A consisting of n positive integers, find the number of its co-prime subsequences. Since the answer may be very large, print it modulo 10 to the 9th plus 7. So you have an array A of n positive integers. You want to find the number of its co-prime subsequences. Okay, you want to find the number of its co-prime subsequences. The number of subsequences that the GCD of all the elements is equal to 1. And two subsequences are considered different if chosen indices are different. For example, if you have 1 and 1, if you choose this one alone, it's a different case than choosing this one alone, and both we counted. So you have three different subsequences. This first one, this second one, or both of the ones. Okay, so we have this array. We want to count that how many co-prime subsequences we might have. For example, if you consider this case, any subsequence, I mean, if you consider this, you want to find the number of co-prime subsequences. So for example, in here, you can have 1 alone, 1 and 2, 1 and 3, or 2 and 3. Right? Or 1 and 2 and 3. So any case would work in this example other than an empty subset, or 2 or 3. So it's going to be 2 to the power of 3 minus 3, which is 5. Okay, so basically we have these numbers a1, a2 to an. We want to find the number of subsets such that their GCD is equal to 1. Well, I say that if we want to do this, I want to solve a harder problem than this. I'm going to do something even harder. Let me also write the bounds. N is up to 10 to the 5th. AIs are also up to 10 to the 5th. AIs and N are both up to 10 to the 5th in this problem. I want to define some CNT of I, or let's say res of I, which is the number of subsequences, and we will never consider the empty subsequence anywhere. So we have the number of. Do we have a volume problem? Can you guys hear me? Okay, so let's continue. So res of I is the number of subsequences with GCD equal to I. So rest of I is the number of subsequences with their GCD equal to I. So I'm gonna solve it for any possible I, not only for I equal to 1. The answer is definitely rest of 1. So in order to solve it, first I'm gonna solve that in how many ways for each I, in how many ways GCD is a multiple of I. First, I solve that in how many ways GCD is a multiple of I. GCD is not necessarily I, but is a multiple of I. In how many ways? So how can I do that? If I count that, if I define CNT of I as the number of elements divisible by I, if I only consider these numbers, if I only consider the elements such that their value is divisible by I, then I'm sure that GCD will be divisible by I as well, right? So if I only consider the elements that are divisible by I, if I only choose from them, their GCD will also be divisible by I as well. So if CNT of I can be easily calculated. For each number, I can have a 4 on all its divisors. They are roots AI divisors, O of roots AI divisors. I have a 4 on all of them, and I say that I increase CNT of them by 1. Then this way, first I set rest of I to be 2 to the power of CNT of I minus 1. And do not forget that for now, rest of I is defined in a way that GCD is a multiple of I right now. Later on, I want to change it to be exactly equal to I. But right now, our GCD is a multiple of I. So if I consider the number of elements which are divisible by I, rest of I will be equal to 2 to the power of CNTI minus 1. Right? Rest of I will be 2 to the power of CNTI minus I. So for now, rest of I means that how many subsets with GCD some k times I. K can be 1 or more than 1. So now I have this. I want to see that how can I turn res from the number of sequences with GCD equal to I, with GCD a multiple of I, to the GCD being I itself. I say that let's consider all the numbers from 1 to 10 to the 5th. 10 to the 5th is the maximum number that we have. I'm gonna start from the end and go backward. Initially, do you agree that for 10 to the 5th, rest of 10 to the 5th, I want to go backward and fix the values of res, fix the numbers, fix the answers or results. I want to fix the results. I want to fix all the resi's. Okay, so I go backward. Do you agree that right now, res of 10 to the 5th is really fixed itself? Because res of 10 to the 5th says that in how many ways GCD is divisible by 10 to the 5th. Because I'm sure that the GCD cannot be greater than 10 to the 5th. When it is a multiple of 10 to the 5th, it is 10 to the 5th itself. So this last one is always fixed itself. Right now it is fixed. So what I do is that I go backward. Whenever I get somewhere, it is somehow similar to induction. I assume that all the races after this one are right now fixed. I assume that all the races greater than this I want to fix res I right now. I want to fix res I. I'll assume that for each j greater than I, for each j greater than I, res of j is fixed right now. So I want to fix res I assume that for each j greater than I, res of j is fixed. I'm coming backward. I assume that all the ones that are greater than it are fixed. So it's just enough for me that for this I have a 4 on all the multiples of I that are less than or equal to 10 to the 5th and subtract their result from my results. So this is basically what I'm gonna do. In order to fix the res array, and by fixing, I mean that from res of I, meaning that the GCD is a multiple of I, making it in a way that the GCD is exactly equal to I will have a 4 I equal to my max n. My max n minus 1. Max n is, for example, defined as max n is the size of the array, so I must start from n minus 1. It is, for example, 10 to the 5th, 1 if 5 plus 20, for example. I start from n minus 1, go to 1, I minus minus. I'll have a 4. I assume that for all the j's greater than 1, the result is really equal to the number of subsets that the GCD is equal to them. So I should then subtract all the cases then that the GCD is a multiple of I, not I itself. J less than or equal to, let me write it in the correct syntax, is less than or equal to, less than capital N or less than or equal to n minus 1, j plus equal to I. And then I say that res sub I say that res sub I minus equal to res sub j. And I say that only with this code, all the reses will be fixed. Only with writing this code, all the reses will be fixed. Because I started from the end each time using induction, I assume that all the reses greater than this I are fixed. And I know that res of I right now is the number of possible subsequences such that GCD is divisible by I. So yeah, if I have a 4 on all the multiples of I and I see that in how many cases they are the GCD, I can subtract them one by one. And then what remains in res of I is the number of ways that GCD is exactly equal to I, not a multiple of I. So this way, after running this code, my GCD will be exactly equal to I. After running this code, my GCD will exactly be equal to I. Not a multiple of I, because I'm having a 4 on all the multiples of it, and I'm subtracting the cases where GCD is that multiple. And this way, all of the reses will be calculated, and at the end, it's just enough for me to report res of 1 as my final answer. Okay, is it clear now? Please, if it is clear again, put a plus in the chat or use the emoji, and it is not clear, let me know to explain it again. Nice. Nice. We can subtract the answer from divisors of I when we go back. Yes, we can also do that. Yes, that's also possible. We can go back and for each one go over its divisors and subtract the rest of itself from the rest of its divisors. That would also work. Yes. Great. So, shall we move on to the next problem then? Nice, thank you. You're welcome. Okay, great. Let's move on to the next problem then. The next problem is Vasily, the beer, and beautiful strings. Well, this problem says that we have Vasily, the beer, loves beautiful strings. String S is beautiful if it meets the following criteria. String S only consists of characters 0 and 1. At that, character 0 must occur in string S exactly n times, and character 1 must occur exactly m times. So, an S is beautiful if it has n zeros and m ones in total. And we can obtain character G from string S with some possibly 0 number of modifications. The character G equals either 0 or 1. G is given to you. So we want to be able to obtain character G from string S by applying some modifications. And how are those modifications? The modifications like this. A modification of a string with length at least 2 is the following operation. We can replace 2 last characters from the string by exactly one other character. This character equals to 1 if it replaces 2 zeros, otherwise it equals 0. For example, one modification transforms the string 01010 into string 0100. Because you consider these 2 last characters, they are 1 and 0. So they will be replaced by a 0. We said that we only replace them by 1 if they are both 0. So they will become 0100. And again, if I do another modification, now we see that the last 2 characters are both 0. So it will be replaced by 011. It will be 011. These zeros will be replaced by a 1. And it is forbidden to modify a string if its length is less than 2. So you have to count the number of strings such that they are beautiful. Okay, so you want the number of strings. You want the number of strings such that. Yes, sure. I will add the problem in the chat as well. This is the statement. So this is 336D, and I will add all these statements in problem description in the video description as well. So we have this string, for example, 010010. For example, each modification is like this. We consider the last 2 characters, and if they are both 0, we replace them by 1. If at least one of them is 1, we replace them by 0. So next time it would be 01000 in this case. Again, after that we have 2 zeros at the end, so they will be replaced by 1, 01. We have 01 at the end this time. They will be replaced by a 0. Again, we have 10. They will be replaced by a 1. Again, we have by 0, and then we have 00. They will be replaced by a 1. So at the end we will get 1 this way. At the end we will get 1. So you are given n, m, and g, and it says that you have to count that by how many strings with n zeros and m ones you can have such that if you apply these modifications over and over again until you get only one character, that character would be equal to G. So you want to see that in how many ways that last character that would remain is going to be equal to G. N and M are up to 10 to the 5th, and G is either 0 or 1. Okay, so now we want to solve this problem. Well, again, as always, we want to start by some observations. Okay, let's start. I'm going to write here. Let's start by some observations. Is there anything that we can really say in here? Is there any observations that you can say? Well, I mean, I want to find some patterns. I want to find some patterns such that I can easily say that if this pattern is in our string, then the final character is going to be 0 or the final character is going to be 1. I mean, I want to get a clue of how the final character will be determined based on the string. Because I cannot do all these operations for all the strings. So I must find the patterns. I must so have a clue that when my answer is going to be 0 and when my answer is going to be 1. I should have a clue of that, when it's going to be 0 and when it's going to be 1. For a fixed string, answer is always fixed. Yes, definitely, exactly. For if you fix the string, the answer is fixed. Yes. If G is equal to 1, then the first character has to be 1. Why? Not necessarily. But you can say that if G is equal to 0, if G is equal to 1, you can say that the first character has to be 0. Because if the first character is 1, then with the rest of the characters, at the end, if it is 1, when we have 1 and something, when we have only 2 characters, there is going to be 1 and something, and they will be replaced by 0. And that is a very, very good example. That was a very good example. We can say that if G is equal to 1, assuming that the length is greater than 1. If G is greater than 1, the first character must be 0. That's a good thing to say. If there is 0 in a string, then it will become 1. Let's find for G equal to 1, then it is only possible when second last state is 0, 0. Exactly. To find the second 0 for exactly. That is a great idea. That is a great idea. So if we have 1, the second last state was 0, 0. So we can say that the first one must be 0 and now the rest must make another 0. Yes, awesome. So the observations are going to be like this. I can say that very similar to what you said. If the first character is 1, then the final character is 0. Then the final character is 0. Let's say that, for example, if this is S, if this string is S, let's define this final character as f of S. Okay, if the first character in S is 1, then f of S is definitely 0. Unless we only have that single one. I mean, if we have, it's 2 cases. If the first character is 1, if it is the only character, if it is only this one, then the answer is 1, f of S is 1. Otherwise, f of S is definitely 0, because at the end we have 1 and something, and when we have 1 and something, they will be replaced by 0. So f of S will be 0. The only counterexample is that if we have only 1, we have nothing other than 1. Now this is a very important observation. So we are sure that if the first character is 1, the answer is going to be 0. Now assume that if not, assume that it is not the case, the first character is 1. Now consider that if the first character is 0. Now assume that if the second character is 1, if the second character is 1. The good thing is that when we get a 1, we know that, I mean wherever in our string that we have a 1, and after it, if after that 1 it is empty, then this 1 will be returned from this part if there's nothing after this 1. If there is anything after this 1, then definitely the answer of this part is 0. I mean, we are sure that wherever in our string that we have a 1, if we consider from 1 to the end, all that part will be replaced by 0. Unless this is the last character. I mean, if we have 1 in our last character, a 1 will be returned. But if this 1 is in any character other than the last character, a 0 will be returned. Right? So this is very important. So if the second character is 1, again we can say that, okay, we have a 0 here, and then we have a 1. We know that if it is 0, 1, they will be replaced by a 1. Otherwise, if there is any other characters here, from these parts, a 0 will be returned, and this 0, 0 will return a 1. So in this case, f of s will be 1. Unless 0, 1 is the only characters that we have. If we have only 0, 1, if after this 1 there's nothing, as I said, if this 1 is the last character, in that case, f of s will be 0. So the counterexample in this one, we have a counterexample of 1. If we have only 1, it is a counterexample because 1 gives 1. In here also, if we only have 0, 1, it's a counterexample because 0, 1 returns a 0. But if we have any additional characters after them, these are correct. So again, else, if the third character is 1. So if the third character is 1, we can say that, again, we start by 0, 0, 1. Again, if in here we have any characters, these parts will be replaced by a 0, and then these 2 zeros will be replaced. These 2 zeros will be replaced by a 1, and then this 0, 1 will be replaced by a 0. So in this case, f of s will be 0. Unless 0, 0, 1 is the only thing that we have. If we have only, again, the counterexample is that if after 1 we have no other elements, then 0, 1 will be replaced by 0, and 0, 0 will be replaced by 1. In this case, we have a 1. So we see that our only counterexamples are if the only one that we have is the last one. So the main observation is this. We must just locate the first one in our string. If we just find the first one in our string, we can easily see that if it will be replaced by a 0 or if it will be replaced by a 1. If it is the last character, it will be replaced by a 1. If it is not the last character, there is anything after that, all these parts will be replaced by a 0. All these parts will be replaced by a 0. And then when we know that we just have a condition of how many zeros we have before that. The parity of the number of zeros tells us the answer. Because if we have several zeros in here, you can see that each time, alternatively, based on the parity of the number of zeros, the answer will alternate between zeros and ones. Because assume that, for example, we have, let's exclude the case that 1 is the last character. Assume that 1 is in the middle in here. We know that all these parts will be replaced by a 0. So we have several zeros. Our string will only have several zeros after this character is removed. So if you have 1 0, the f of it is 0. If you have 2 zeros, they will be replaced by 1. So the answer is 1. If you have 3 zeros, these two will replace by 1, and then with the last 0, it will be 0 again. If we have 4 zeros, these 3, as they saw, will replace by 0, so the whole thing will be replaced by 1. And you see that each time by adding an additional 0, it will just toggle. Because whatever the last one is, when we add a 0 to the beginning of it, it will toggle. So it will be again 0. So it is completely based on the parity of the number of zeros, because each 0 can toggle the final answer. So if we have these ones, yes, we are considering the first one, the leftmost one. So all the things before it are zeros. All the elements before it are zeros. We are only considering the first one. Because we said that if you consider the first one, everything after that can be easily determined what they are. Everything after that, I mean, we can easily see that what it will be replaced by. Assume that this is not the last index, then we know that this part will be replaced by 0. Then we have several zeros, and when we have several zeros, we can easily see that if they will return a 0 or they will return a 1. And if the first one if the first one is the last one, this is the case that we have only 1 1 and it is as the last element. In this specific case, these parts will not be replaced by a 0. This part will be replaced by a 1. If we remove everything other than from 1 forward, we can replace it by a single 1 because it was from the initially a 1 itself. So in this case, we have several zeros and ones, and then if you consider this 0 1, they will be replaced by a 0. So again, we get to the points that we have several zeros. So the point is that the main thing is that in our problem, we can just fix, when we want to count that in how many ways we get g, we can fix that where is the first one. And as I said, based on where is the first one that you have, you can see if your final answer will be 0 or 1. You can see that at the end you will get 0 or 1 based on the position of the first one. Based on the position of the first one, you can find out if at the end you will get 0 or 1. So you can get if it really gives you g. Okay. If it gives you g, you add all the possible ways that the first one is in here to the answer. And now I'm going to talk to you about how can we count. How can we count? In how many ways? The first one is at position I. So we want to count that in how many ways we can count, how we can count in how many ways the first one is at position I. But the point is that first you can find out if it gives you g or it does not give you g. If it does not give you g, you will skip it. Otherwise, you will count that in how many ways you can have your first I here and add that to your answer. We will talk about these parts, that how can we count. But is it clear so far? So far, is everything clear? Can you make a sheet of set of questions that help us to improve and grow in competitive programming from newbie to candidate master? Yes, I will definitely do that. Yes, sure. I will work on that. And I can maybe share it on Discord or Telegram. You can join our Telegram channel from this link if you want. Let me send you the link of the Telegram channel. I will do that and add it in our Telegram channel. It might take a little bit time, but I will definitely work on that. I will try to do that. Okay, so you can join the Telegram channel here. If I find the sheet, I will definitely send it to you. You're doing great job. Thank you very much, dear chat. Thank you very much. It means a lot for me that you're watching it. I hope that it helps all of you. It is really meaningful for me if it is really having effects on you, and it gives me motivation to continue and even doing it better. And guys, I would appreciate it if you like the videos, you can share it with others such that others can join and attend these live streams as well. I think that would really help this work to be seen by more people. Yes, the stream will be saved, yeah. Okay, so far it's clear, no one has any questions. If no one has a question, we can just now continue and talk about how can we calculate this. This is the total number of ways that we have. But now we want to find that in how many ways the first one is at the specified position. So let's talk about it. We want the first one at this specified position. But it is easy to calculate that how many ways we have, because we are sure that before it everything is 0. So we have n zeros and m ones in total. Assume that there are x zeros in here. So in the remaining parts, everything till this one is fixed. So for these ones are fixed. We do not make any change. We have one way for that part. So the point is that, and in the rest of it, we have n minus x zeros here and m minus 1 ones here. We have n minus x zeros and m minus 1 ones. So we can easily just have a combination. I mean, we can choose that at which positions these m minus 1 ones are. So it would be a combination, a binomial. It would be, in total, the length of here is n minus x plus m minus 1. Choose m minus 1. We can choose that in which positions we have 1. And then if we have those positions, in the rest of them, there will be zeros. And this is all the ways that this position is the first one. So we are literally just fixing that. How many zeros will you have before your first one? If your m is 0 and you have no one, that's easy, right? Because you have only n zeros, you have only one way, and you can see that if it gives you g or it does not give you g. And we know that when we have zeros, based on the parity of the number of zeros, you can see what we can say. In here, we said that if you consider the first one, the leftmost occurrence of 1, based on that, you can find the final g. So we fix that. We fix that how many zeros are before the leftmost one. And when we fix that, we have n minus x other zeros and m minus 1 other ones. So we have only a combination to find out that how many are there. And how do we calculate combination? How will we calculate this value? We know that n and m are up to 10 to the, let me show it to you in here. They are up to 10 to the 5th. N and m are both up to 10 to the 5th. So these values are up to 10 to the 5th. How can we calculate this combination then? As we said in our previous session, we can use Fermat-Litter theorem to calculate all the inverses of the factorials, and using Fermat theorem we can have divisions. So because n choose k is equal to n factorial over k factorial, n minus k factorial, this would be a problem that how can we have division when we have everything modulo mod. In the last session, we talked about that we can have division using Fermat. A modulo b, a divided by b, modulo mod is congruent to a times b to the power of mod minus 2. Why? Because b to the power of mod minus 1, modulo mod, is 1. Therefore, we can just multiply any number by b to the power of mod minus 1. And because it is only 1, it does not change anything. By multiplying it, nothing would change. So when you multiply it, it would not change modulo mod. So this b to the power of mod minus 1 will be divided by b. We will have b to the power of mod minus 2. So basically this number, modulo mod, is congruent to n factorial times k factorial to the power of mod minus 2 times n minus k factorial to the power of mod minus 2. And power is explained how to calculate power in the previous topic stream as well. If you need to watch those parts again, you can watch all the topic streams in this playlist. Let me send you the specific topic stream. In here you can watch these parts again. So yes, this is how everything can be calculated in this problem, and using these combinations we can find all the number of ways that we will get g. So basically the main observation, the key observation was that we have to fix the first index of 1. That was the main important thing that we had in this problem. So is everything clear? If you have any questions, you can ask about this one. If you are completely okay with that, please again put a plus or use this emoji. If you are okay with that, let me know, so that we can move on to the next problem. Yes, the number of ones and zeros were fixed. Thank you for random emojis. So, is it clear? Then, if nobody has any issue, we can now maybe move on to the next problem. Okay, thanks, Auran. So, let's move on to the next problem then. And thanks, Ruitas. Thank you very much. I think we have some delay as well, so that would be a bit problematic. So let's move on to the next problem. The next problem is, well, first of all, let me first say this. There is a theoretical problem that I wanted to tell you first before talking about that problem. Let me first state this theoretical problem. Assume that you have some x and you want to find the number of possible numbers that you can choose, like y from 1 to n, such that GCD of x and y is equal to 1. So basically what I mean is this. Assume that you have some fixed n. N is, for example, up to 10 to the, for example, 6. And you have some q arrays as well. Q is also up to 10 to the... For now, let's forget about the q arrays. Assume that you have only one x. You have only one x, and you want to see that how many y's from 1 to n, how many y's from 1 to n exists such that, how many y's from 1 to n exist such that GCD of x and y is 1. Okay, so you want to find that how many y's from 1 to n exists such that GCD of x and y is equal to 1. And you can then now consider that, for example, this is q arrays. You have q arrays on x. For example, you have q arrays. Q is also, for example, up to 10 to the 6 or 10 to the 5. In each q array, you are given an x. And you have to say that how many y's exist such that GCD of x and y is equal to 1. Well, how can we solve this problem? So this is the question that we want to answer. How can we find the number of such y's? Well, again, in here, basically, we have to first see that when we fix some x and we want to find out how many y's exist such that GCD of x and y is equal to 1, we have to consider all the prime factors of x. For example, let's say that x is something like this, some p1 to the power of alpha 1. This is the prime factorization of x. Some p2 to the power of alpha 2, and some pk to the power of alpha k. If GCD of x and y, GCD of x and y can be even we can even write it like this. We can just write it in brackets, and this also means GCD of x and y. GCD of x and y is equal to 1. It means that y is not divisible by any of the pi's. So it means that if GCD of x and y is equal to 1, it means that y is not divisible by any of the pi's. Okay. And we know that the number of pi's is a little. I mean, we said it previously. When our number is up to, for example, 10 to the 6, when our number is up to 10 to the 6, we have at most 7 prime factors. At most 7 prime factors. So k is at most 7. Why we have at most 7 prime factors? Because assume that we have 8 prime factors. If we have 8 prime factors, x must be at least the product of 8 smallest prime factors. It's 2 times 3 times 5 times 7 times 11 times 13 times 17 times 19. Right? This is going to be the 8 smallest ones. And we know that, as we said previously, for example, 2 times 7 is at least 10. 3 times 5 is at least 10. And this 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 is at least 10. So it is greater than 10 to the 6. These are all greater. We have 6 numbers that are greater than 10. It's better if I write it strictly greater than 10. So these numbers are greater than 10. So x will gonna be greater than 10 to the 6, which is a contradiction. So we can say that when x is at most 10 to the 6, we will have at most 7 prime factors. And now we want to find out that in how many ways y is not divisible by any of the pi's. If y is not divisible by any of the pi's, its GCD with x is 1. Otherwise, its GCD with x is not 1. So what we can do is this. We have these prime factors. We have P1, P2 to PK, P1, P2 to PK. We want some y such that y is not divisible. We want to find the number of y such that y is not divisible by pi's. Well, the first approach that comes to mind is to subtract them one by one. So we can say that we have n ways in total. We have n possible numbers in total. Our number must be from 1 to n. How many of them are divisible by p1? The number of numbers divisible by p1 is going to be n over p1. N over p1 of them are divisible by p1. Right? So we can subtract them because they are bad ways. And n over p1 of them and n over p2 of them are divisible by p2. And so on. N over pk of p sub k of them are divisible by p sub k. So the first thing we can say is that it must not be divisible by any of the numbers, so we subtract them one by one. But is it the final answer? Is it not correct? Is really the number of y's that their GCD with x is equal to 1, or in other words, the number of y's that are not divisible by any of these pi's, is it really equal to this number? Well, as you might know, it's not. Because maybe your number is divisible both by p1 and p2. If your number is divisible both by p1 and p2, then you are decreasing it once in here and once in here. So you are decreasing it twice, but it was just added once in here. So you have to add it back again to make it, zero, to make it have no effects. Exactly. This is right. In the case of 0, it will be double counted for 2 and 3. If your number is divisible by 6, in here you will once count that it is divisible by 2, once count that it is divisible by 3. So you will decrease it twice, but they must have you must have decreased it once. So the point is that the numbers that they are divisible both by P1 and P2, they must be added back. So how many numbers do you have that they are divisible by P1 and P2? Because P1 and P2 are both prime numbers, they are co-prime. So if it must be divisible by P1 and divisible by P2, it means that it must be divisible by P1 times P2. So the number of them is n over P1 times P2. And you can say that for any other two indices as well, P1 and P3, P1 and P4, P2 and P3, and all the way up to Pk minus 1 and Pk. So they must be added back again. So is it correct now? It is still not, because if you assume that some number is divisible by P1, P2 and P3, once, some x is divisible, some number like z is divisible by P1, P2 and P3. You counted it once here, you subtracted it 3 times in P1, in P2 and in P3, and then you added it back again 3 times for P1 and P2, P1 and P3, and P2 and P3. So right now it is counted once, but it must not be counted. So you have to again decrease it once again. So you have to again decrease n over, if your number must be divisible by P1 and P2 and P3, it must be divisible by the product of them. So it must be divisible by P1 times P2 times P3, and so on again. And again, you can see this pattern that if you consider 4 numbers, they must be again added, because if you consider 4 added numbers, first they were added in n, so they were added in n once, and then you have P1, P2, and P3 and P4. For each one single one of them, they are subtracted here. So you have 4 choose 1 subtractions. And for each choosing of 2 of them, they are again added in here. So you have 4 choose 2 ways to add them here again. And then for each choosing of 3 of them, they are subtracted. In this case that you are subtracting them. And you can easily see that this number is always equal to 1. Okay, so this number is minus. This number is equal to minus 1. Because in here, if you see it, it has 1 minus 3 plus 6 minus 4, 1 plus, I said 3. 1 plus 4 minus 1 minus 4 plus 6 minus 4, it is minus 3. You can see that always for even numbers, this number is leads to minus 1, leads to minus 1, which means that you have to add it once again. You have to add the case that they are divisible by P1 to P4 once again. And when you calculate these numbers for odd numbers, this number will be plus 1, which means that you have to decrease this number once again. So because we know that always the effect is going to be minus 1 or plus 1, so we have to make them 0, because these are the cases that these numbers are divisible by at least one of P's. So we have to either decrease them again or add them again. So this is how we can calculate these numbers. So now the question is that, okay, if we do this, so this is the name of this approach, as you might be familiar with it already, is inclusion-exclusion. I didn't go in depth to prove everything. If you want, we can have a session dedicated to inclusion-exclusion and discuss everything related to it. But for now, I just explained to you in that what does it mean. I will also include a link in here such that if you want, you can read about it. This link of Wikipedia can work. I'm sharing it here in the chats. I will also add it in the description. You can read more about inclusion exclusion in here if you want. But this is inclusion exclusion principle. So now, this is not only mathematics. It can be even used in programming. We can use it to solve this problem. The point is that you are going over all the possible subsets of PIs. So the point is that when you want to count that for how many y's do you have, such that it is not divisible by P1 or P2 to Pk. How many y's do you have such that it is not divisible by P1, divisible by P2, all the way to divisible by Pk. Well, it means that you can have a for on all the possible subsets of PIs, and see that in how many ways your y will be divisible by that subset. You do not care about the rest of them. So you have several PIs. You will see that in how many ways n is divisible by those ones. It's equal to n, the number of those numbers is n divided by the product of those p's, those pj's that you're considering in this subset. And then if the size of the subset was odd, you have to decrease it from your answer, like in here. N over P1 was decreased, N over P2 was decreased, N over choosing 3 ones were decreased, N over choosing 5 was decreased. So you see that if you see these signs, it's based on how many PIs are in the denominator. Okay, it's based on how many PIs are in the denominator. So you can just see that, you can just say that your answer is going to be based on this N over the product of PIs. And if the size of the subset was odd, we will subtract that from the answer. If the size of the subset was even, we will add it to our final answer. And this way we can just see that what is the number of ways that your y will not be divisible by any of the P1 to Pk. Okay, is it clear? Number of 1 to choose, yes. I think you are you are saying that for this part, that we showed that it is equal to -1 or +1. Yes, if we go in depth to prove this, we can talk about it. But I wanted to quickly just mention this. And basically we wanted to focus in solving this problem. But guys, if you want, we can have a dedicated session for inclusion, exclusion, and just talk about this. We can prove it, etc. And solve so many problems using inclusion, exclusion. So this is how we can find out that how many numbers we have from 1 to n such that GCD of x and that number y is equal to 1. So let's now solve another problem from Codeforces. Guys, if you have any problems, you might ask as well. So if you want, if you have any questions, you can ask right now. Otherwise, we can now just move on to the next problem. The next problem is this one. I send it in chats. 1750D. This problem says that you are given two integers n and m and an array a of n integers. For each I from 1 to n, it holds that ai is from 1 to m. Your task is to count the number of different arrays b of length n such that bi is from 1 to m for each I from 1 to n, and GCD of b1 to bi is equal to ai. So you want that for each prefix, it means that these ai's are GCDs of the prefixes. So for each prefix, you know that what is the GCD. You know that GCD of b1 only itself is equal to a1. So it means that b1 must be equal to a1. GCD of B1 and B2 is equal to A2. GCD of B1 and B2 and B3 is equal to A3, and so on. So you know the GCD of each prefix. You want to see that how many possible arrays B do you have such that the prefix GCDs will be like this. Okay. So, for example, in this case, you have 4 to 1. Your main array can be 4 to 1 itself, or 4 to 3, or 4 to 5, for example. So this is basically what you want to count. And n is the sum of n over all test cases is at most 2 times 10 to the 5th. And your m is also up to 10 to the 9th. Your m is the bound on AIs and also for BIs. BIs are also up to m. And it is up to 10 to the 9th. So in here we have the prefixes, the GCDs of the prefixes. But initially we know that for I equal to 1, for I equal to 1, why this happens? For I equal to 1, we know that B of 1, B of I, which is B of 1, is equal to A of 1. This must be true, because the first one must be equal, either way. If you consider the next elements for I greater than 1, we can say that B of I must be in a way that GCD of A of I minus 1 and BI must be equal to AI. I mean, we said that GCD of B1 to BI must be equal to AI. It means that GCD of B1 to BI minus 1 is equal to A of I minus 1. So we can replace them by A of I minus 1. B sub I must be in a way that GCD of A of I minus 1 and B sub I must be equal to AI. So the case where I is equal to 1 is easy. It has one way, it doesn't contribute anything. So we just need to calculate the number of ways that we have for BIs, for I greater than 1, and multiply the number of ways by each other. I mean, for each one of them, we see that how many ways do we have and multiply these numbers, because these numbers are really independent. For each I, we should find the number of suitable I's that have this condition, and then we will multiply them by each other, because these are completely independent of each other. B of I does not really care about the other B's. It only cares about GCD of them, which is a constant value, is equal to A of I minus 1. So it doesn't care about the other BIs. So BIs are independent. Each one of them can be calculated and they can be multiplied by each other. So now we want to find for each I in how many ways, how many BIs we can have, how many possible BIs we can have. And definitely, again, this is a trivial case. There's a trivial case that if AI is not a factor of A of I minus 1, if A of I minus 1 is not divisible by AI, then the answer is 0, definitely. So we do not consider these trivial cases as well, because if for each I, AI was not AI minus 1 was not divisible by A sub I, the answer is 0, definitely. So this case is solved. For this case it is 0 and there's no doubts about it. But if I is greater than 1 and all these AI minus 1s are divisible by AI is a factor of AI minus 1, this means that we must have A sub I minus 1 must be equal to some, for example, K1 times AI, and B sub I must be equal to some K2 times AI. So AI minus 1 must be K1 times AI, BI must be K2 times AI, and the GCD is equal to AI. So basically it means that GCD of K1 and K2 must be 1. In other words, both of these numbers must be divisible by AI, and if we divide them by AI, the GCD of that division must be 1. So basically we want GCD of AI minus 1 over AI and BI over AI to be 1. We want this. Okay. And let's call this as CI. Let's call this as C sub I. we want to choose, if we choose Ci, Bi is determined as well. So it's kind of, we want to find the number of possible Ci's. Because if we choose Ci, we just need to multiply it by Ai and we have Bi. So we want to see that how many Ci's do we have. And for Ci, we know that Ci must be a number from 1 to m over Ai. It cannot be greater than m over Ai. It is at most m over Ai. And GCD of Ai minus 1 over Ai, let's call it, for example, some Zi as well. This is, for example, some Zi, just for simplicity. GCD of some Zi, which is a fixed number, and Ci must be equal to 1, right? We have our numbers in a way that we have some Zi's. We want to choose Ci in a way that GCD of Zi and Ci is equal to 1. We are given Zi, we have to find out in how many ways we can fix Ci. And this can be easily calculated. This can easily be calculated using what we said in here. This was exactly the problem that we were talking about. So we have all the prime factors of Z. Zi is equal to, again, P1 to the power of alpha 1, P2 to the power of alpha 2, 2 Pk to the power of alpha k. Ci must be a number that is not divisible by P1 to Pk. We can have inclusion-exclusion over R subsets, and if they are even size, we will add them to the answer. They are odd size, we will subtract them from the answer. So our order will be 2 to the power of k. And since k is relatively small as well, 2 to the power of k is okay time complexity. Because our Zi is equal to Ai minus 1 over Ai. So it is up to m. And we know that we have at most, because m is up to 10 to the power of 9, again we have so many few prime factors for it. It has at most, for example, 9 prime factors. If a number is at most 10 to the power of 9, it has, for example, it has at most 9 prime factors. And if we consider these 9 prime factors, we have 2 to the power of k solution. We have 2 to the power of 9 of 2 to the power of 9 solution to have inclusion-exclusion on them, going over all these subsets, and add or subtract the answer that gives us to our answer. So our total time complexity will be equal to O of n times 2 to the power of k, where n is up to 2 times 10 to the 5th, and k is up to 9. So in this time complexity, we can solve this problem. Is this one clear as well? Does the solution to this one make sense too? If you have any questions, you might ask right now. Nice. I hope that you enjoyed this topic stream so far. If you wanted to support my work, you can like the video or subscribe to the channel, and especially share this video with others that you know, and you might think that these live streams, these topic streams are useful for them as well. I think it would help a lot if you can share it with others as well. And it was like always, it is always a pleasure to have you in these topic streams. I would really love to see that we have these live streams that has some effect on some people. I hope that it continues to have effects. As always, we're gonna have topic streams on Fridays, and I hope to see you back again on the next topic streams as well. I'm gonna put a poll on our Telegram channel each week. You can find the link of the Telegram channel in our description of in the description of this video or in the YouTube channel. Let me also send it here as well. This is the link of the Telegram channel. If you want, you can join there, and each week we have a poll to choose the topic stream. And each week we have these topic streams. I hope that it would help you out. Thank you, Aaron. So Thank you very much again for joining. Hope to see you next time as well. Goodbye, guys. Yes. The exclusion, you asked that the inclusion takes k times 2 to the power of k. Yes, you're right. It would have some k as well, I think, yes. But in total, it's gonna be okay. I think that you're right. I think it takes k as well. Yes, we can also do that. We can use prime factorization of b. Yes. So thank you guys. See you next time. And tomorrow is a CF contest, and that CF contest will be streamed by us as well. I think either me or my friends who are helping me are gonna stream tomorrow's contest as well. So see you guys.